Hi you guys, my name is Steven. I'd like to welcome you back to my calibration channel. I'd also like to welcome back my ISO gum experts, Carl and Maddie. In addition, I want to thank you for clicking one extra click and following me over to YouTube. Normally I do my stuff in LinkedIn, but LinkedIn has a 10-minute time limit on videos. I want to take just a few extra minutes to nail down today's topic. And that deals with the fact that the gum uses calculus to derive sensitivity coefficients. Most of the stuff I post online is the result of my 30 years experience in the pharma business sector. 10 of those years I spent carrying a bag as a calibration technician. The word passion is used a lot today. I'm not going to use it. I will say I'm completely convinced that if we're smart enough to do calibrations for a living, we're smart enough to thoroughly understand and use the gum. Even though it's not particularly well written as far as we're concerned, nor is it even internally consistent. So if we take just a few minutes and work together, I think we're going to see some immediate benefits. One is we're going to build a sensitivity coefficient from the ground up. We're going to talk about why are they important, and in fact, why are they critical sometimes. We're also going to see problems that cannot be solved any other way other than using a sensitivity coefficient. Lastly, and most importantly, we're going to see that they're actually pretty simple to understand and use. Now, I'm not saying there's not barriers and challenges when we go forward. I'm just saying that to me, the biggest barrier in this area is fear. Here's what we're going to do with fear. I've got more good news. We're not going to use the gum while we talk about this particular area. Instead, we're going to use a wonderful document that was written by one person, not a committee. This person said explicitly that he wanted to help not only experts, but newcomers navigate their way through the gum. Now, I'm talking, of course, about the romantically titled M3003 from the United Kingdom Accreditation Service. If you will go and Google M3003 space UKAS, you will immediately see a free PDF that you're welcome to download and use. And it's a wonderful companion piece to the gum. As a matter of fact, if you print it out, you can go right straight to page 15 because I'm going to go right there and pick out a perfect example of how sensitivity coefficients are derived. I say it's perfect because it's simple and it's elegant. So let's get into it. First thing we're going to do is a thought experiment. Now, if you've seen my other videos, you know that I love thought experiments. One reason I like them is because they're really cheap, and that's good for my budget, because I don't have a very big budget here at Stephen Pereira Enterprises. So let's say you're at work, and a group very near you has just completed a project where they made some measurements so they could estimate the height of a flagpole. Here's a schematic that they used. They measured the base repeatedly. They measured angle theta repeatedly. Now in high school, I got a D in trig from Colonel Tebow, but even I can tell you that the nominal height of this flagpole is just the length of the base times the tangent of angle theta. I've got more good news. Not only did the team working near us give us a schematic to show us what they did, they also gave us a look at their data. And they told us, look, angle theta was 37 degrees plus or minus half a degree. The length of the base, after we measured it many times, was 7 meters plus or minus a tenth of a meter. Now that gives us a nominal height for this flagpole of 5.275 meters. That's not the problem here today. The problem is, how are we going to support this measurement by assessing the uncertainty of the measurement system using the gum method? Okay, so let's proceed. The first thing the gum wants you to do is construct a mathematical model for your system. At the very least, you need to start with a functional description of your system. Now, we can do that right with what we know already. We can just create an equation that says h, or the height of the flagpole, is a function of two variables, the base, d, and the tangent of angle theta. We can add other uncertainty elements to this model later on, but this is a perfectly reasonable way to start. Now, I've never had a calculus class. Maybe you never have either. So we owe it to ourselves to try and cheat. We might at this point say, well, look, we got two measurements. Let's just calculate their standard uncertainties, add them together in quadrature, and motor on. We'll pretend calculus doesn't exist or enter into this problem. Here's two fundamental reasons why you cannot do that. First of all, when you think about the uncertainty budget, you know that you can only have one set of units in it. The measurement of the base is in meters. The measurement of angle theta is in degrees. Clearly, the uncertainties that are attached to these two measurements are going to have different units. We can't proceed. There's another more subtle reason why we cannot just add these in quadrature. The height of the flagpole is the product of two other variables, not the sum of two variables. Whenever you have that condition, you have to assess the contribution of each of these elements as they go together to make the measurand. In short, these two elements are not statistically independent from each other. They're correlated. In fact, they're correlated in a fundamental sense, which is they are multiplied together to produce an outcome. We can't ignore the sensitivity coefficients in this application. Okay, since we can't ignore them, let's just get into it. Now the GUM says, by definition, that the sensitivity coefficient, C sub I, is equal to the partial derivative of f divided by the partial derivative of all of the variables. Okay, I'm a visual learner. Before we freak out over the fact that there's Greek letters in our future, I at least want to see where do these quantities live in relationship to each other according to our schematic. So let's take a look. Here is F. F is the output for our system. It's also called the measurand. So the partial derivative of F speaks to the variability of F that's caused by the variability of the things that go together to make the F. The same thing is true for the base. The partial derivative of the base just speaks to the variability of the base measurements. Same for angle theta. Now at this point, I've got some other really good news. In almost all cases, when we attempt to do sensitivity coefficients, we can re-express this calculus in a very simple algebraic relationship. So instead of the partial derivative of f, we can talk about the delta of f. We already know the delta of f because the team before us has already given us the limits of the measurements of the height of the flagpole. The same is true for the base. The partial derivative of the base is equivalent in this case, in almost all cases, to delta, the measurement of the base. The same is true for theta. So what we need to do here is produce two sensitivity coefficients. One discusses the relationship between the varying heights caused by the varying measurements of the base, and then we need to do the same thing for angle theta. Now when we're considering each of these relationships, we're going to hold the other variable steady. Now we've already got the numbers we need to do this. So first, let's consider the relationship between the base and the height of the flagpole, or F. So we can say that the height of the flagpole varies according to the measurements of the base, and notice we keep angle theta the same. So this comes out to two expressions. We can simplify those and combine them into one, which is 0.15 meters divided by 0.2 meters. Now, this simplifies one step further to 0.075. Notice that the units drop away. Now we're going to do the same thing in terms of angle theta while we hold the base steady. We're going to see the same relationships created by two very simple statements of the variability in the height of the flagpole caused by the variability in the angle theta. That's what sensitivity means. It means how sensitive is the output to the thing we're considering. Okay, so we can simplify again in the same way we did the first time. Only this time what we come up with is 0.192 meters per degree. Notice that the meters per degree doesn't drop out. Now, is this going to mess us up when we go ahead and do our uncertainty budget? We'll just have to wait around and find out. Now the next thing that happens is the author of the M3003 gathers together everything we know so far so that we can make one more very simple calculation for each contributor to our total uncertainty and come up with standard uncertainties for each of these elements. So let's go through this matrix. First, we're going to talk about the uncertainty caused by the measurements in the base. We already know that variability. Now, what's with the rectangular distribution? From a strictly frequentist point of view, we have no data at all. Therefore, we can't speak to its variability. We can't speak to its random behavior. We have no data to look at to perform a frequentist analysis. That means we're in the type B data world. We're taking data from another group and processing it further. Those are the perfect conditions, especially since the team gave us the limits of these measurements. That's the perfect time to use the rectangular distribution. When we use the rectangular distribution to do estimates of probability, we always divide by the square root of 3. That's what the square root of 3 divisor is. Next, we see our sensitivity coefficient that we already calculated for ourselves. The last step on this first line is to calculate the standard uncertainty on the basis of what we've learned so far. So we just divide the variability of this line item by the square root of 3 and multiply it by the sensitivity coefficient. That allows us to come up with a statement of uncertainty for this element of 0.433 meters. Okay, now let's proceed to the angle theta, which is the second contributor. We know its variability. We know that we're going to predict the probabilities based on the rectangular distribution for the same reason that we used it the first time. So the divisor is the same. Here is that funky sensitivity coefficient that still has units in it. But when we perform the same steps that we did in the first line, we notice that the units straighten themselves out and we end up with a description of the uncertainty of angle theta expressed in meters. That is one of the very powerful things that sensitivity coefficients do for us. They straighten out problems with mixture of units. So now we have two line items. What's with this third line item? Now remember, according to the frequentist approach, we have no data. So we can't assess anything about the dispersion of that data. It would be tough to state the uncertainty of this measurement if we knew nothing about its dispersion. As a matter of fact, the team that made the measurements assessed this for us. They said, you know, these measurements that we did repeatedly, they look like they distribute normally. In fact, we even estimate the dispersion of that uncertainty as 0.5 meters based on a normal distribution. Almost all attempts to do a measurement repeatedly will distribute normally. So that makes sense to us. Now what we have is three elements in our budget. We're ready to add in quadrature and come up with a combined standard uncertainty. So that's what we do. We arrive at 0.863 meters. We're only one step away from total victory. So let's take that step. We already have a nominal measurement. Now we're about to expand the combined standard uncertainty and express our assessment of the uncertainty of the system that came up with that nominal value. So there it is. This is really cool. We couldn't have done it without sensitivity coefficients. So let's summarize. If you ever have a budget line item that's the product of two other elements and not the sum of two elements, those elements that made up that line item are not statistically independent from each other. They are correlated. You have to do sensitivity coefficients in that circumstance. And we've seen how easy it is to do. If you ever get to the point where you're starting to line up your budget items and you see different units, you need a sensitivity coefficient to convert one way or the other. We saw how easy it is to do, so I recommend you do it. Perhaps the most fundamental thing and most important thing we've seen is that for most cases, when you do have to do sensitivity coefficients, you can do a very simple algebraic expression using delta instead of using the partial derivatives. This is true in almost all cases. Now, when it's not true is a subject for another video, but suffice to say, people do this all the time. Now, we can do it too, but we can do it understanding how do we get to do it and when to watch out for little gotchas. They're not going to occur very often, but we do need to know how do we get to make this shortcut. I really enjoyed making this video. As I said, I had to overcome my own fear because I've never taken a calculus class, but I truly believe that when we work together, we can overcome that because we have no choice. We have to go forward with using estimates of measurement and uncertainty in more and more places, and that's a good thing. I want to thank you for your extra attention to this. If you have any comments or questions, please feel free to leave them. I will see you back in LinkedIn whenever my topic can be squeezed in under 10 minutes. In the meantime, thank you very much.